So we're going to continue this process. Here we go. Write the adjacency matrix for this graph and state the degree of each vertex. So this is going to be the same as what we've done. It's just a little extra practice. So A, B, C, D, E. A, B, C, D, E. Here we go. And let's just glance at it very quickly and point out something that's fairly obvious. A doesn't go to itself, B doesn't go to itself, C doesn't, D doesn't, E doesn't. So this diagonal right here, this main diagonal technically is what it's called, is all zeros. So let's fill this in very quickly with ones, and then everything else will become a zero. A goes to B and to D. A goes to B and to D. B goes to A and to D. B goes to A and to D. C goes to E and only E. D is A, B, E. Oops, D is A, B, and E. And E goes to D and C. D and C. All right, everything else becomes a zero. And it also said state the degree of each vertex, which I think will be very easy to do once we have the adjacency matrix. Again, let me point out a pattern here. This row and this column read the same. So 0, 1, 0, 1, 0. 0, 1, 0, 1, 0. And that works for now. This one, things change. So here goes. The degree of A is 1, 2. The degree of B is 1, 2, or 1, 2, either way. The degree of C is 1. The degree of D is 3. The degree of E is 2. The degree is really going to come in handy later on. It's one of those things where it's like, why do I even need to know that at this point? But later on it becomes important. So we're going to create the adjacency matrix for this, wonder what goes in the blank. This is called a directed graph. It's directed because, well, there are directions. And, excuse me, this one has arrows, as you can see. So let's back up for a second. In this case, A goes to B, B goes to A. That's just implied by the way the line or the segment is drawn. But here, A goes to B, but B doesn't go to A. So there is no reciprocity, I guess. So it's like an airplane flight from Asheboro to Boston, but Boston doesn't fly to Asheboro. So A, B, C, D, E, and then A, B, C, D, E. All right, and again, I'm going to go for the obvious. Actually, on this one, I am going to very quickly do this, just because this one's, even though it's the same size as the last one, I have this feeling that things are going to get a little sloppy if I don't do this. There we go. All right. So here goes. None of them go to themselves, but A goes to B and A goes to C. B does not go to A, but B goes to C and E. C goes to D. D goes to E. And E goes nowhere. You cannot travel from E to anywhere else. This one's kind of neat, actually. If this was a game, for example, if this was a game and you start here, then you could go here or here, and then you go here or here, and then you go. Basically, as you travel, no matter how you move, you're eventually going to end up at E, and E absorbs all the movements. So it's going to travel and go to E, and it's stuck there. So it's not going to go any further. And so when I talk about the degree of these, and it did not ask, but if I did talk about the degree, then I would say the degree of A is 2, and the degree of B is 2, not 3, because this arrow is pointing to B, but not away from B also. So the degree of A is 2, the degree of B is 2, the degree of C is 1, the degree of D is 1, and the degree of E is 0. Once you get to E, you're trapped. There's no way out. Okay, now we're going to go a little bit backwards. We're going to start with an adjacency matrix, and we're going to draw a vertex-edge graph. So I'm going to zoom in just a little bit more. And all of these have 5 vertices, A, B, C, D, and E. And we are going to just go A, B, C, D, E. Here we go. And we're going to just connect what needs to be connected. Oh, let me back up for a second and then point out something halfway obvious. On this one, and I've said this before, the row, column are the same. On a directed graph, they are not. Okay, check it out. 0, 1, 1, 0, 0. 0, 0, 0, 0, 0. The A row and the A column are not the same. The B row and the B column are not the same. All right, so if I have a directed graph, then the rows and the columns are not necessarily the same. So if I have rows and columns that are the same, then it is not a directed graph. This will make sense in a minute. Anyway, A goes to B and B goes to A. So we're going to just do this. This is not a directed graph. A only goes to B. That's the only place you can go from A. B goes to A, C, D, and E. B goes to A, C, D, and E. All right. C goes to B. C goes to B. Done. C goes to B. I'm sorry, D goes to B. D goes to B. And D goes to E. There we go. And E goes to B and D. And again, notice that all the rows and columns correspond to one another. They are equivalent in a sense. And therefore, this one does not have arrows. So if I look at this next one, this one does have arrows. And here's why. Here's one thing that gives it away. A doesn't go to B, but B does go to A. So for that reason, I'm going to need arrows on this one, not on this one. So it's a good way to look at it and figure out what you need and what you don't need. So let's just draw A, B, C, D, E. E. There we go. We're going to go one letter at a time. So A goes to D. A goes to D. Not a straight line, but that's all right. And it goes to D, so it's an arrow. So again, D doesn't necessarily go to A. If it did, we'd put an arrow on that one too. Again, this one's a directed graph because the rows and columns do not read the same. All right, B goes to A. B goes to E. All right, C goes to B. D goes to E. I'm looking right here. D goes to E. And E goes to A. E goes to A. E goes to B. E goes to B. So this arrow goes both ways. Okay? E goes to B and E goes to D. So this arrow also goes both ways. All right. So let me just state a few things that are not obvious and maybe not even necessary, but if this was some sort of game where you start at a particular place, first of all, once you leave C, you're never coming back. There's no way to get back to C. Once you leave C, you can go here, you can bounce all back and forth, but there are none of these vertices, also called nodes, by the way, N-O-D-E-S, none of these vertices that would absorb all the movement. For example, E has no arrows that come out of it, which I said this a minute ago, but therefore E would absorb whatever comes its way. It goes here, it can travel all kinds of fancy ways, and it eventually gets to E and it can't get out. Here, once you move away from C, you can go here, you can go, you can't go there. You can go here, you can go back and forth here, you can go, but you're not trapped on any particular vertex. It's just something that's good to notice.